Great. So thanks again for the invitation to speak. It's always lovely to be asked to talk about your favourite topic, which is what I'm going to talk about today. And I could go on all day about this. I've got 45 minutes, I'm told, although we're running behind schedule. So I'm just going to do this, and if I'm talking too much and you're sick of it, just tell me and I'll stop, all right? Well, when worlds don't collide. This is going to be a bit of a wander through 20th century history along the way. But essentially what I'm talking about here is some applied respiratory physiology, in particular applied to inhalational anaesthesia. And specifically I'm going to talk about ventilation and blood flow matching in the lungs. The technical term for this is ventilation perfusion inhomogeneity, but I prefer to call it VQ scatter because it's much easier to say. To summarise, VQ scatter has significant effects on lung gas exchange and the efficiency of lung gas exchange. It affects the pharmacokinetics of the agents that we give our patients to breathe to keep them asleep. And it becomes significant during general anaesthesia for reasons we'll talk about in a minute, even in relatively healthy patients. So VQ scatter reduces the efficiency of lung gas exchange, and it's the cause of the arterial to alveolar differences, the AA differences that we can see in our patients on a routine daily basis. These sorts of numbers, an entitled CO2 of 32 and an arterial CO2 of 47, are not uncommon in our patients under general anaesthesia, I think you'd agree. So I'm going to take you back to 1944 at the height of the Second World War, and with thousands of young men flying at high altitude for the first time in human history, the US Army Air Force took a great interest in understanding the physiology of altitude. And this led to a huge drive. They had their best and brightest brains working on trying to understand the physiology of lung gas exchange with more expertise than had been the case before. One of those leading lights was Richard Riley, and the three-compartment model of VQ scatter is often referred to as the Riley model. And the three-compartment model essentially divides the lung up into three compartments, obviously. You've got shunt at one end, you've got dead space at the other, and you've got what is sort of rather quaintly referred to as the ideal compartment in the middle. The reason why it's such an appealing model is because it lends itself to some very simple mixing equations which we can use to easily calculate these indices. So, these haven't reproduced very well. That should be VD dot and VT dot on the left-hand side. So dead space fraction is easily calculated by measurement of an arterial CO2 partial pressure and a mixed expired CO2 partial pressure using the Boring-Hoff equation. If you want to focus on alveolar dead space specifically, then that equation is modified by measuring an alveolar or an end-tidal CO2 instead of a mixed expired CO2, but the principle is the same. This is the diagram out of Riley's chapter in West's textbook, and I think it's actually a more elegant diagrammatic description of these concepts, where both alveolar dead space and venous admixture are essentially can be depicted as shunts, shunting of ventilation and shunting of blood flow around the ideal compartment where ventilation and blood flow meet. This is a diagram out of Nunn's textbook, which is a slightly more anatomical description of what's going on, but essentially alveolar dead space is a segment of lung which is ventilated but which is effectively receiving no blood flow for various reasons. Now, in fact, John Nunn's group in the 1994 published what I think is one of the classic papers in respiratory anaesthesia physiology. They actually wanted to look at the partial pressure cascade for isoflurane. And of course, as Jan has already mentioned, there is a partial pressure cascade for anaesthetic agents, which is very similar to the partial pressure cascade for oxygen, which we're all familiar with from the textbooks. And they were interested in looking at the components of the inspiratory to arterial difference, which effectively is that difference generated by uptake of isoflurane by the lungs, alveolar capillary uptake. So, small group of patients, 6 patients, cannulated with an arterial line and the PA catheter, and they measured inspired and expired gases, arterial mixed venous blood, and cardiac output at minute ventilation. And this was a meticulously conducted study. It's a beautiful paper. It's full of just a wealth of beautiful data. So they calculated the alveolar dead space fraction using the Bohr equation and found that it was about 12%. These patients were patients under general anaesthesia with healthy lungs, and that's a pretty typical sort of figure, I suppose. They also thought that they'd do the same calculation measuring isoflurane partial pressures instead. Same patients, same lungs, same equation, but the dead space for isoflurane, the alveolar dead space, is not 12%, it's 60%. How can that be? I mean, the alveolar dead space is what it is. It's that segment of lung which is ventilated but effectively not perfused. And to be honest, the leading lights in anaesthesia physiology, the guys who write the textbooks, were at a complete loss to explain how this could be. This was a mystery to them. And I think that's a pity for reasons that I'm going to talk about as I go. The problem with the three-compartment model is that it tells us what the lung doesn't do. It doesn't tell us what the lung does do. And in fact, the problem is with this ideal compartment, because what it's saying is that there's a box which has uniform VQ ratio. It's a single box. All the gases go into it. All gas exchange occurs in this box. It's really a one-compartment model. It's not really a three-compartment model at all. All these compartments on either side do is tell you how big that box in the middle is. So the problem is that the lung doesn't look like this at all. It doesn't look like this, it doesn't look like this. The lung actually looks like this. This is what ventilation perfusion ratios in the lung actually look like. What we call physiological log normal distributions, which means that if you plot VQ ratios on the x-axis, you guess, and it's a logarithmic scale, you guess Gaussian or normal shape distributions or approximations of those. And the log standard deviation of that distribution can be measured as an index of the degree of VQ scatter that's occurring in the lungs. All right, so I'm going to go back 20 years now to 1974. The American jets looked like this. A brand new anaesthetic machine, interestingly, looked like that. You can see the military are always way ahead of us, can't you? And the computer in those days looked like that. And a couple of very clever expatriate Australians who left our shores and went to California to UCSD and basically created the modern generation of respiratory physiology as we know it. They invented something called the MIGET, the multiple inert gas elimination technique, which by infusing six volatile substances intravenously and then measuring the concentration in arterial blood and in expired gas, you could actually measure the VQ distributions in the lung and generate distributions just like this. A very clever technique which exploited a wide range of solubilities of the gases that you were administering to the patients. And they showed that you could actually predict lung gas exchange with quite high precision if you were able to measure these distributions using the MIGET technique. Now, what about anaesthesia? Well, fortunately, a clever and innovative group of Swedish anaesthesiologists, not long after, were able to use the MIGET technique to show us what happens to the lungs in general anaesthesia. And they showed that the progression from the awake state to the anaesthetised state was associated with a significant increase in VQ scatter using the MIGET technique, which is, and I must say, I've lost count how many times I've quoted these references in my talks and papers. Now, the thing is that Peter Wagner, in 1974, on the basis of the physiology of the MIGET technique and what they understood about all this, he could have told you that gases of different solubility are going to have different AA gradients. It's the basis of the MIGET technique. And he could have told you that you could expect that the AA difference for isoflurane and the alveolar dead space for isoflurane are going to be completely different to that for CO2. He knew about this. For some reason, we didn't know about it, even though isoflurane is our gas. Right? You'd think that in a specialty where dealing with gases which have a wide range of solubilities and different pharmacokinetics, you'd think that we'd be a bit more switched on to this issue, but it went under the radar screen. Now, part of the problem was that these guys were respiratory physiologists. They weren't anaesthetists. They were interested in exercise physiology and altitude physiology. They were more interested in annapurna than anaesthesia. And they weren't talking to us, or we weren't talking to them. There was a real disconnect here, which I think was a pity because it sort of held things up for quite a long time in terms of our progressing our understanding of the pharmacokinetics of the gases that we use on a daily basis. When I got into this game 20 years ago or more, my computer looked like this. I had more hair. 10 years later, my computer looked like this, and the computing power was about 100 times what it had been earlier. But doing this sort of, understanding the way that these sorts of issues work is relatively simple, and modelling it is a relatively simple thing to do. It's not about computing power at all. What you're doing is in each compartment in the lungs, you're computing mass balance for the gas, for each gas, using the familiar Fick equation, which is the mass balance equation that describes alveolar capillary uptake of any gas, and applying it to all the compartments that you want to model. Now, you can model 23 compartments or 53 compartments just as easily as 3 compartments with a computer. And in fact, when you set up a model to actually look at these things, you need to generate log normal distributions like this. So on this side, we've got a lung with relatively little VQ scatter, where the ventilation distribution and the blood flow distribution almost overlap, as opposed to one on the right here where the ventilation is diverging to the right and the blood flow is diverging to the left. Then you can set up, this is my model, right? And you can add all sorts of bells and whistles, but the underlying principles are very simple. You're computing the Fick equation in all those compartments and summating them and working out what overall gas exchange for each gas is. These are the sort of models that the respiratory physiologists were using for 20 years before I started doing it. All I did was start adding anaesthetic gases to the mix, as well as oxygen and CO2. And sure enough, what you could show, even with a model such as mine, is that you could predict that as VQ scatter worsened or increased, the difference in alveolar dead space between CO2, what you calculate with carbon dioxide, and isoflurane progressively ramps up. VQ scatter worsens, the difference gets bigger and bigger. Very predictable from what are really underlying simple models. So we could have explained Landon and Nunn's findings quite easily if we'd been involved in the whole process. And the reason is because the lung doesn't look like that at all. But they didn't seem to understand that. So what? What's the implications of this for our daily practice? Well, probably not a lot, to be honest. But if you're considering doing research on the pharmacokinetics of the agents that we use, or getting a finer understanding of their pharmacokinetics and lung gas exchange, using the 3-compartment model has a lot of potential dangers. And I'm going to illustrate that with my favourite gas, nitrous oxide. And I know I've talked about this before, and I don't want to labour the points, but I'm just going to talk again about the second gas effect, because it illustrates this very nicely. As we all know, nitrous is administered in the high inspired concentration. There's an initial very rapid uptake of the gas, which declines with time. And in 1967, Stolting and Eager described how this would produce, this rapid uptake of nitrous oxide from the alveolar compartment in the lung would produce concentrating effects on the other gases, on the oxygen and the volatile agents, the second gas in the alveolar compartment. And they used this classic diagram, which you'll still find reproduced from time to time in the textbooks, of this lung compartment where half the nitrous oxide is taken up. And what that does is it increases the concentration of oxygen and second gas from 19% to 32%, from 1% to 1.7%. It's a concentrating effect. Very simple explanation of the phenomenon. Now you can see what I'm getting at here, can't you? This is our old friend, the ideal compartment, at work again. one big box where everything's happening. And when you've got a weak model, you are leaving yourself open to criticism and attack very easily. And there are a lot of sceptics who immediately picked all the holes out in this and said, this can't be right. C.Y. Lin was one of the most vocal of those critics, and in Anesthesia Intensive Care he published a very nice summary of what we understood about the way that these gases behave in the lungs, and pointed out that the uptake of nitrous oxide, the alveolar capillary uptake of nitrous oxide after induction, peaks at quite a low level. He calculated it to be about 250 mils a minute and then starts to gradually decline from there. And that the concentrating effects that that level of uptake of nitrous oxide would produce would be very, very small. Nothing like Stolting-Eger's diagram, nothing like this 50% uptake of nitrous oxide. In fact, this level of uptake is about 5% of alveolar ventilation. So the concentrating effects would be perhaps a tenth of what this diagram is suggesting to be the case. And in fact, Stolting-Eger's diagram, if you want to be quantitatively correct about it, should look like this, where there's a tiny decrease in the size of the compartment with uptake of nitrous oxide, and the concentrating effects are trivial, probably only about 5% increase in oxygen and second gas concentrations. So they said this is a much more realistic depiction of the second gas effect. It's a trivial thing. We shouldn't be paying any attention to it. And actually, and he was quite right. Within the limits of the model that we were using, he was absolutely right. And this is all happening in the context of a gradual erosion of the place of nitrous oxide in clinical practice. The pros and cons I've summarised here, but the second gas effect was one of those pharmacokinetic advantages that was traditionally quoted of nitrous oxide use. And if you could pour a bit of throw a bit of ammunition at the second gas effect, then it was strengthening the case for removing nitrous oxide from routine practice. So there was quite a number of papers and letters and commentary published over the years, all based on this premise that nitrous oxide, the second gas effect, was actually a trivial or non-existent phenomenon, and all based on that model. And this was actually a battle being fought in a toy kingdom that doesn't actually exist. Because the lungs, Lin was right about the nitrous oxide uptake, quite right, but the lungs don't look like this, the lungs look like this. I repeat myself. So if you model the second gas effect using a realistic distribution of ventilation and blood flow, realistic VQ scatter, what do you get? So this is the data that my model has generated, which was actually part of my PhD thesis, and I've just reproduced it here to show you how these things really work in the lungs. So these are distributions of ventilation, which is the green curve, and blood flow, which is the red curve, and you can see that this is a lung with a moderate amount of VQ scatter. So the ventilation's going to the right, the blood flow is going to the left. These are the high VQ compartments, these are the low VQ compartments. Now the uptake of nitrous oxide is distributed, that's the blue curve at the bottom. So this is, I haven't made this up, this is what the model generates when you compute all those. This is 20 compartments that we're modelling here. And you can see that the nitrous oxide uptake distribution follows blood flow very, very closely. Doesn't follow ventilation, it follows blood flow. Right? Uptake of all these soluble gases is perfusion-driven uptake. This is how our gases are taken up by the lungs. It's driven by blood flow through the lungs. And all the action occurs in these lung compartments with moderately low VQ ratios, because that's where all the blood flow is. But you can also see that the ventilation to these compartments is really very poor. Right? They have low VQ ratios. So the concentrating effect that uptake of nitrous oxide produces in those compartments is very powerful. It's very powerful. Now these are the lung compartments which get the majority of the blood flow. So these are the lung compartments which determine the content of blood leaving the lung, going to your brain and putting you to sleep. So what happens to the sevoflurane, the second gas? in this model. So the dotted line is the predicted uptake of sevoflurane if there's no nitrous oxide present, and the solid line is uptake of sevoflurane in a nitrous oxide oxygen mixture. So the difference between those two curves there is the second gas effect. You can see where it's occurring. It's occurring in those well-perfused, moderately low VQ compartments, and it's a powerful effect. At least that's what the computer models predict. And of course, your three-compartment model won't tell you any of that. It'll just be misleading. So what do we see when we actually collect data from patients? This is the paper we published in Anesthesiology some years ago. If you look at the second gas effect on alveolar or entitled partial pressures, you get this sort of curve where this is the rate of rise of alveolar partial pressure versus time, and the heavy line is the nitrous oxide group, and this thin line is the group which just received sevoflurane in oxygen. So the difference between those two curves there is the second gas effect. And it's a very modest effect. It's a boost of about 10% in the rate of rise of sevoflurane, entitled sevoflurane partial pressures. And that's very consistent with previous studies. Jan and Andre have done a very similar study, and so has Ted Eager. However, I remind you that VQ scatter leads to AA differences for all the gases that we've administered to the patients. And it's arterial partial pressures that matter, it's not end-tidal partial pressures. So what do we see happening to arterial partial pressures of sevoflurane? This is what happens. The increase, the second gas effect on arterial partial pressures is much, much stronger than that you measure in end-tidal partial pressures. It's about almost 25% as opposed to 10%. So the second gas effect on arterial partial pressures, which is invisible, of course, to us in clinical practice, is much more powerful. And that's driven by VQ scatter. So there's probably ways to do this better without having to engage in complicated models with 20 compartments. One simple way is to modify the original Stolting and Eager diagram. First of all, you add blood flow to it. So we've got our second gas effect here with the concentrating effect pushing up the second gas concentration from 1% to 1.7%, and there's 1.7% in blood leaving the lung. And let's turn it into a two-compartment model. That's pretty simple. It's actually simpler than a three-compartment model, actually. And let's then distribute the blood flow unevenly between those two compartments and let the uptake of nitrous oxide follow the blood flow. And what you end up with some simple arithmetic, is just what we've shown with our complicated model, a more powerful concentrating effect in blood leaving the lung than what's reflected in the alveolar entitled gas. So you can use sophisticated computer models, or you can do it very simply on the back of an envelope like I've done here and predict the same effects, at least qualitatively. So I'll just conclude with a few sort of general remarks about this whole field, which sort of strike me in my work on this over the years. As I said, VQ scatter is pretty fundamental to the pharmacokinetics of the agents that we use. The concept of MAC has been a useful clinical tool, but I have to say, in terms of understanding how our agents behave in the presence of VQ scatter, it's been a bit unhelpful, because really the place of considering and measuring arterial partial pressures has sort of been lost. And that's not meant to be an indictment of Ted Eager and his contribution to the field, which has been fantastic. But certainly I think it's an issue you need to consider if you're looking at doing pharmacokinetic research of any sort on inhalational agents. Here's a bit of a tantalising sort of thing I'll leave with you as a final little point. If you measure the effect of VQ scatter on the rate of rise of partial pressure of two gases with very different solubilities, this is what you find. I find this quite tantalising, and it's something I intend to pursue with some clinical study. I've modelled here the rate of rise of sevoflurane partial pressure and ether. And I've done that. I chose ether because it's much more soluble, obviously. It's got a partition coefficient of 12 as opposed to Sevoflurane, which is 0.7. But they both have a MAC of 2%. And what this diagram shows is the divergence in partial pressures that you get with increased VQ scatter. So this line here for Sevoflurane is an ideal lung with no VQ scatter, and then these two lines are the alveolar and the arterial partial pressures you would get if there was significant VQ scatter happening. So that's what happens to Sevoflurane, that's what happens to ether in the presence of VQ scatter. You get that divergence away from the ideal line. Interestingly, the effect on the modern, less soluble agent is greater than it is on the old-fashioned ether in terms of the effect on the arterial partial pressure, right? The arterial partial pressure is what puts you to sleep, not the alveolar. I find that quite interesting, and you won't get anybody telling you this when they're trying to sell you a bottle of desflurane or Sevoflurane, I can tell you. I suppose from the point of view of clinical practice, MAC is useful because it ignores the arterial partial pressures. It just tells us to look at the alveolar partial pressures. That's what we measure, end-tidal gas. And, well, that's what we do and it works. We know it works. But the underlying pharmacokinetics, I think, are quite interesting. So in summary, I'll just finish up by saying that there's a lot of dangers in doing research, whether it's pharmacokinetics or physiological research into our field, relying on simple models. And I think you need to tread carefully and certainly consider using more sophisticated models. And as I said, you can model 23 compartments just as easily as 3 compartments with a computer. So it's food for thought. Thank you very much.